Serial communication over wires is one of the easiest and simplest ways for two devices to exchange information that are in reasonably close proximity. It also works over longer distances, but there are some complications to that I won't go into here. The main principles apply, but there are some details you need to know. Right now, we'll discuss in-room, or at least in-building, serial communication, which also includes in-device. You can have two chips wired up and use serial communication to exchange your bits and bytes. But the basic principle is that you exchange one bit at a time, one after another, in a sequence, in serial. Sort of like hooking up batteries in serial. Versus parallel, where you have them all sharing inputs and outputs. Communicating in parallel is multiple pins all at the same time, sending a set of bytes at a time. Now you would think that would be faster, and technically it is, all other things being equal. But as it turns out, serial ends up usually being the superior method of communication, simply because you can have higher quality parts if you have fewer of them. For example, electroplating gold onto connectors. Well, gold is really expensive, but you're not using much gold, so it doesn't appreciably change the cost of the connector. The same thing here. If you're only using a couple wires, they can be really good wires. Also, they take up less space. It's cheaper overall. The parts required to drive the serial interface, to write the bits, to read the bits, is itself cheaper and smaller, and reuses a whole bunch of parts, such as a clock, from the rest of the system. IDE for disk drive interface was replaced by serial ATA. USB is probably the most ubiquitous serial interface in the world with just 4 pins, power and ground, and 2 data lines, which is the absolute minimum you need to drive a device by serial. So many things in life have become serial for communication just because of its simplicity. So let's explore it. So we have 2 devices. These can be chips on the same motherboard. These can be, your computer and a printer. These can be your computer and a mouse. These can be 2 different parts of a robot talking to each other. It can be any 2 devices that want to communicate by serial. So you have your power and ground to each of these devices, and you're going to have a transmit and receive pin on each. So this will be transmit, this will be receive. Transmit is abbreviated TX and receive abbreviated RX. And we'll say the RX is here and the TX is here. Unsurprisingly, the transmit on one is connected to the receive on the other. The transmit on the second is connected to the receive on the first. This is what's called a full duplex connection. You can send and receive both directions at the same time. And we need some power. So there's a power source and another. So we'll just connect the positive power in there. And then we'll do something interesting. The negative power, the ground, the 0 voltage, will all connect to each other. So each of these devices has their own power source connected to the positive terminal, which can be batteries, it can be a wall wart, it can be your USB plus 5 volts wire, it can be any power source, DC of course, but the ground pins are connected. Now why would we do that? Well, the way this works is the transmitting device sets a voltage, and voltages, as we know, are differences. You don't just have a single wire with a voltage on it. I mean, technically you can have an electric charge on one end of a wire trying to establish an electric field, but it's not going to do anything. You have to have a circuit, you have to have current flow for a device to do anything with a voltage. So say you set your TX here, your transmit, to the positive. So 5 volts for USB perhaps, which means it's measured relative to the negative terminal. The positive connection is here, the negative is here. Measure transmit from here to here, and that is your voltage. If you had this 0 as a low, then it would be connected to the negative, and then you measure from the negative to the negative, which is 0. But this thing is doing the reading. This is setting the voltage relative to this ground, but this is reading the voltage relative to this ground. But they're the same, you say? No. Voltage is created by applying a positive and negative electric charge, forms a field, and then we say the voltage across the power source is the voltage of the power source. This might be, let's say these are both 1.5 volt batteries. This could be 1.51 volts. This could be 1.47 volts. Both basically fully charged batteries completely within operating range. But can you see why there might be a problem measuring relative to each other? It'll work, you can, but it's going to give you a different wrong voltage because you're not using the same reference, right? This is 1.51 volts apart, which means this will be 1.51 volts apart, but this won't be. So what you do is you hook one end, in this case the negative end, together, and it tends to even out. And there can be current flow. It's called a ground loop. Don't worry about it for now. In these normal situations, it's minuscule. In worst case, you could use some sort of star arrangement and have resistors that simply resist the flow of this ground current, but there really shouldn't be that much if you're using proper power supplies, proper modern power supplies. So the way it works is this device transmitting sets a voltage relative to the ground, and this one is using the same ground to measure that voltage, and it varies over time. How does it vary over time? Let's demonstrate. So let's graph voltage and time. This is time, which starts at 0, and this is voltage, which goes from 0 to whatever, let's say 5, if it's USB. Now, of course, you've seen graphs like this when we're talking about alternating current. It goes up and down, up and down. This is direct current. And so let's say we want to change the voltage with a regular frequency. Let's call it baud rate. So let's say we're going to use 9600 baud. 9600 baud. That means 9600 bits per second, but not data bits because there's overhead involved. The overhead is bits too. It's 9600 total bits, including overhead, per second. Now, 9600 is quite slow in modern terms. As components have gotten faster, dealing with processing more data at a time, components have gotten higher quality, wires have gotten higher quality, shielding has gotten higher quality, the baud rates keep going up and up to the hundreds of thousands. A simple Arduino can do a couple million, but 9600 is a fairly common one. Now, what does that mean? Well, there's sampling. Let's say here, at a regular time interval, in this case measured in seconds, it would be 1 divided by 9600, 1/9600th of a second. So we measure at these points. This is the receiver. The receiver at a particular point will measure the voltage coming in on its receive pin, which is the transmit pin from the other side. We'll measure the voltage, which will be high or low, within its ranges, and it will say that is a 1 or a 0. The transmitter is the one that sets the voltage. So let's say, we're up here and nothing's really happening, but then it goes down here and across, and it goes up, across. Like I said, I'm not a draftsman. But basically what happens is the sender is varying the voltage over time between high and low. The receiver is sampling the voltage at specified time intervals. So in the middle here, so we got a high, a low, 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 high, high, low, high, low. Ones and zeros. So how does it know when to sample, how often to sample? You simply set that value. You set your modem to 288K speed. You tell your computer your modem is using 288K speed. You just have to set that on both sides so that they both do the same thing. How does it know to sample here instead of here where it's changing? We'll get to that in a moment. But something to go over first is that nothing is perfect in life. I believe we've mentioned that, including clock chips. You can get the best quality clock chips in the world, but none of them will be absolutely perfect. So how does this thing stay in sync over seconds, minutes, hours to make sure it's always sampling where it expects to? It doesn't. That's what some of the overhead is for. Every time it sends a chunk of bits, it resynchronizes. Let me show you the problem. So our transmission is supposed to be 9600 baud, but we have two devices. Let's say this one, the one that's sending, is 9601. That's the best it can do. That's the closest it can come to exactly 9600 based on its clock chip. A deviation of 1 per second is really, really, really freaking good. Trust me, it is. Let's say our receiving end is 9598. Again, it's really close. And you might think that's such a minuscule difference. It matters, though. So here's our time again. And so let's say you have a quiescent line, and then the transmitter is like, oh, I have a thing to send, and it sends it there, right? So this one has been waiting. So it wants to synchronize, right? It's just sitting there waiting for this one to do something. The receiver sees something happen and says, okay, I'm going to start there. So they're perfectly in sync. And so this one is sending, and it's sending the best it can at 9600 baud. And this one is receiving the best it can at 9600 baud. But you'll see this one is a little slower, just a little bit slower. So this sample is over there, and then over here, and over here, over here, over here, over here, over here. I've exaggerated it, obviously, just to show you the point. But you can see there's a drift. No matter how close they are, they're not going to be perfect, and there will be a drift. The better quality, the less drift, the more bits you can send before resynchronizing, but it will still need to be resynchronized. So you see how it's synchronized here? I'll show you how it does that, and it just does that repeatedly. But that's the problem we're trying to solve. So let's plot our voltage versus time again. We have time, we have volts. So when the line is quiescent, when it's doing absolutely nothing, nothing's happening, it's high, essentially a 1. And this will go on for as long as it needs, it's just high, it stays there. The transmitter just has its voltage set to high and is not doing anything, it's just ignoring the serial port if you're not sending anything on it. The receiver is sampling this continuously. In fact, it's sampling it faster than the actual baud rate. If your baud rate is 9600, it might be sampling it at 15,000 or 100,000 or whatever it can muster. Because just sampling and checking for a high is much easier than actually processing bits with a protocol. So it doesn't need all that circuitry and it can do it really fast. And that helps with the synchronization because you have sub of a baud window. Remember, like 1/9600th of a second? If it's sampling higher in order to synchronize at the start, it can get closer to that exact moment and then start using the clock chip to time. But the point is, when the line is doing absolutely nothing, it's just up here, high. Now, why high? Wouldn't you think it'd be better to have it low so that it's using less power? 2 reasons. One is legacy, back in the telegraph days, the teletype or something along those lines. Basically, if your idle is high, if nothing's happening and it's high, and then a tree falls on your line, then you'll notice that it's just continuously low. And that can't happen, because if it goes low, then something's being transmitted and it's going to go up and down. It's guaranteed to go up and down, in fact. I'll show you that. So if it goes 0 and stays there, you know your line is dead. It's not really much of a problem nowadays, but that's part of it. Why we don't bother changing it? Well, first of all, people in the electronics field hate change in all of its forms. But, setting aside my snark, a lot of the time people use MOSFETs. MOSFETs are a type of transistor that work in a special way, which I'll eventually do a video on. But basically they are incredibly energy efficient when they're not switching, which means they're not opening and closing, they're just sitting open or sitting closed, which means a high or a low is on them. If they're just sitting there on high or sitting there on low, it's basically the same thing and they're doing very little. So because of the components we use, because of the invention of the MOSFET, it doesn't matter that this is sitting high, the MOSFET is still not leaking very much. So it doesn't matter. So we may as well just leave it this way. So what happens? Let's say this is the moment that the transmitter says, I want to do something. So the transmitter changes the voltage. It goes, boom. So the voltage goes low. This is called a start bit. There's always one start bit. A transmission is detected by an idle high line going low. And because this thing was timing, the receiver was timing, and it detects, okay, once it gets about down to here, it says, okay, this is actually going low. It's not just line noise. So it says, okay, it's going low, and I know it's at 9600 baud. So I know that it's taken such and so time to get there. Now it's there, so I'm going to say here. So the receiver decides that is a safe point to start sampling, right? And the transmitter, of course, knows about how long it needs to hold this level for the sampling to occur. That's how it synchronizes. The transmitter switches the voltage, and once it has, it says, I have to hold this for 1/9600th of a second. And it does, and then after that period, it can switch again. And the receiver says, okay, the voltage has settled, so this is going to be there for 1/9600th of a second. So I'm going to sample at maybe, let's say, half that, or whatever. Maybe 2/3, something like that. So then, the clocks are synchronized. This one, the transmitter was already synchronized, and the receiver has decided how to synchronize based on that first start bit. Now, we get to the specification of a serial connection. So we were at 9600 baud, and we say 8N1. 8 is how many data bits we're sending in a packet. That's nice, that's a byte. You can have fewer if you want for whatever reason. Maybe you don't need to send that many. Maybe you have a ton of signal noise, or maybe your clocks are really crappy and they have to resynchronize a lot. For whatever reason, you might send fewer. So we have data bits. So let me compress this a bit. In fact, let me redraw it so we don't take up so much space. So our voltage was high, and then the moment the transmission started was there. The transmitter brought the voltage low and held it for 1 bit's width, whereas the receiver saw that and decided this is the sampling spot. So then it's like, okay, data bit 1, 2, 3, 4, 5, 6, 7, 8. So it'll measure the changes. So this was our sampling point for the start bit, right? So now there's always 1 start bit. So we specify there's 8 data bits. So we have those 8 data bits sampled, and it's whatever. And then let's say the last data bit was a 1. Whatever your data bits are, we already showed how you sample those. Now, the N means no parity bit, and E would mean even parity bit, and O would mean odd parity bit. Parity is an error checking mechanism that worked back in the day but doesn't work so much now. Let's say that your datum is as follows: 1 1 0 0 1 1 1 0. How many ones do we have? 1 2 3 4 5. 5 ones. So if we're looking for an even number of ones, then the parity bit will be 0 because that's an odd. 0 is false. 0 is not an even number of parity bits. If we're looking for an odd number of parity bits, the parity bit will be 1 because there are an odd number of ones. That's just another thing you communicate between the devices. You just configure your transmitter and receiver and you say 9600 8 in 1 or whatever. So that's how parity bits work. They count how many ones, and based on whether it cares if it's even or odd, it sets the parity bit. Now, there are 2 reasons this doesn't work now. I mean, it does work, you can use it, but it's not really practical and not useful. It just wastes a bit, really. First of all, it doesn't detect errors well anymore with higher transmission rates. Think about it. The faster you're transmitting, the more bits you're cramming into 1 second, the smaller they are in time. So some transient signal noise, like a squirrel took a dump on a power line, your neighbor turned on their vacuum cleaner, something caused noise on your line and garbled part of your transmission. The more bits are crammed into a space, the more likely those bits are to be flipped in groups rather than one at a time. Parity is great at detecting single bit errors because flipping a 1 to a 0, 0 to a 1 will change even to odd. And back in the day, slower time intervals for the bits meant more likely that an event of signal noise would affect only 1 bit. But think about flipping, or not flipping, or whatever, garbling any number of bits. What is the chance of recalculating the parity with these garbled bits and getting the same parity bit back out? It's 50%, because it's only 1 bit's difference between even and odd. If you have a group of bits flipped in essentially random ways, for all that you care, it's random, then there's essentially a 50% chance of whether or not the parity bit will even detect that error. So that's already a big problem. The other problem is the parity bit does not help with recovering from the error. You may need to retransmit the data. You may need to say to the other side, yo, stop, reset, start again. Modern protocols like TCP/IP on the internet have a built-in better checking function that checks the data of an entire packet at a time. So if the packet gets garbled, the checksum will be wrong. It will not match. If the checksum is garbled, it won't match the packet. Either way, it works. So it's a better error detection. And it includes a built-in protocol for renegotiating the sending of the data again. So your parity bits in a modern setting with high transfer rates are bad at detecting errors and don't help you fix it anyway. So it's really just a waste of bits you could be using for data. But you can use it if you want, and it's just another bit right here. You just have another bit. It's timed it based on the start bit, and then it counts how many data bits it's expecting, and then it counts 1 more if you have a parity bit set. Feel free to turn it on if you like. It can't hurt anything because if you have no errors, then the parity bit will always match and you'll be perfectly fine. You'll just transmit your data more slowly. But let's not worry about the parity bit anymore. Now we have what are called stop bits. There are 1 or 2 of these. There can be 1.5. You can negotiate whatever that your systems both support, but the common values are 1 and 2. What is the purpose of a stop bit? Remember how I said it has to resynchronize? Well, it synchronized the first time by saying, okay, the line has been high for a long time and it just went low. The start bit is always 0, no matter what. It's always idling high and the start bit is low, so it always knows a high to low transition start, and it times there. And then, of course, it's getting more and more out of sync here, but, this many bits is perfectly fine. Well, your stop bit, let's say your first one, is a 1. It's always a 1. The same as this. The stop bit, or bits, let's label it stop bit, stop bit. You could have 2. It's the same high level. It's always going to be high for the idle. It's always going to be low for the start bit. It's always going to be high for the stop bit. But the stop bit, from the transmitter's point of view, the stop bit is bits that it transmits. Since, okay, I have 2 stop bits, I'm going to send a 1 and a 1, and then it starts again with the start bit to 0. Or if that was the last transmission, it just leaves it high. But from the receiver's point of view, stop bits don't technically exist. It doesn't matter, they're just there. So because once it has counted out the number of bits it's supposed to receive, and it says the stop bits are starting, it just stops. It goes back to this logic. It says, okay, the line is quiescent. I'm going to sample at a high rate and look for a start bit. The stop bits and the quiescent line are the same thing. If this was the last transmission, the line would stay quiescent, the same as the stop bits. But if there's another transmission right after, then you're going to have your next start bit, which is going to go low, and it does the same thing again. That is the magic that it synchronizes every single time. From the transmitter's point of view, it transmits the stop bits, and then it continues transmitting the start bit and the next byte, or whatever clump of bits you have specified. But from the receiver's point of view, the line is quiescent, a transition to low is a start bit, it times out the receipt, and then the line is quiescent again. It's as if the transmission is starting and stopping for every chunk, logically anyway, however you might do that in circuitry. And that's how the resynchronization timing works. It's really quite brilliant, isn't it? Now you might say this is wasteful. The start and stop bits, we've established why we need them, but surely there's a better way. Well, no, there's a different way. You might consider it a side grade. If you add another wire, in fact, another wire per direction of transmission, you get rid of the start and stop bits. In fact, you even get rid of the negotiation. You don't have to worry about baud rate or anything like that. I'll show you. But of course, now you have more wires, more circuitry. So it's a trade-off. Do you want faster transmission? Do you want more flexible transmission? Or do you want cheap transmission? Let me show you the other way. So just like before, we have our power for each device. We have our common ground for each device. And we have our 2 lines. Now before, this line would transmit in this direction, and this line would transmit in this direction. Voltage is relative to the common ground. But we're not doing that now. This one is now transmit and receive, and this one is clock. This is now a half duplex connection. The data can only go this way. If you want full duplex, then you need 4 wires. So what happens here? Well, first of all, the same thing for the transmit line. That's no different. To send a 0, you have a low voltage. To send a 1, you have a high voltage. But this thing is not doing any timing. You have not negotiated baud or anything. This clock signal, it's sitting high or low, whichever works for your device. And that's the quiescent. Let's say it's sitting high. So it's always 1, just 1, 1, 1, 1, 1. Quiescent line doing absolutely nothing. This one is reading that it's a 1 constantly, and it's waiting for something to happen. So let's say you want to send a 1. So you have this line at a high voltage, and then once you know this line is at a high voltage, you bring this one down to low. Transition. This one sees the transition from high to low, and as soon as it detects that, it samples this and says there's a bit, but only that bit. And now this clock is low, and this thing is not going to continue to sample. It samples when it goes from high to low. They call that the falling edge. So it's not going to sample when it reaches 0. It's going to sample as soon as it sees it goes from 1 to 0. So the clock goes back to 1, and the receiver is doing nothing, and then it wants to send another 1. So the clock goes down again. This one says, okay, it just went down, sample it. Set this to 0, goes up and down 3 times, it gets 3 0 bits. And you can transmit bits at any rate that you want, and it's all data bits. And it's generally called a clock line because you're powering it with a clock, because you're transmitting as fast as you practically can. So you just hook it up to your clock with a frequency divider if you need to slow it down. But that's the other way to do it. You essentially double the wires, unless you only wanted one directional transmit in the first place. But in that case, you would have had 1 wire, so you're still doubling the wires. So the normal way, for a full duplex connection, you have 3 connections. Your transmit one way, your transmit the other, and the common ground line. If it's in the same device, then that's only 2 wires because you're all on the same power source. If this is, over a USB cable, then you're sharing the ground wire in the USB cable. But this one, you've got your shared ground, so that's 1, and then you've got 2 for each direction, so it's 3 or 5 wires. But it's a whole lot easier, isn't it, to at least think about. You just set your voltage and you just tell it, okay, now. So it just depends on your application. Most applications are not going to need that flexibility. And the regular protocol, which uses fewer wires, will be just hunky-dory. But this is also fairly common. Now, there are more ways to do it, and I'm going to super briefly go over them, or perhaps even mention them, because they're much more rare, much more involved, and I can go into more detail in the future if necessary, but generally, these two methods are all you will ever need. So, a third method does not use a shared ground. In this method, these are completely separate power sources, just like they normally would be, being two different devices and all, just like that, and you have your two wires. But what are these wires? Well, we could call this one TX plus and TX minus. This one could be RX plus and RX minus. Remember how voltage is a difference, and on the transmission line we had to measure it relative to ground, which is why we needed the common ground, so they were both measuring relative to the same ground. Well, there's no more common ground, but we're measuring not to the ground, but between each other. So for example, if you apply a high voltage here, let's say you're 5 volts, and a 0 voltage here, you're going to have a positive voltage measuring from here to here. So you could say that's plus 5, you could say that's a 1. If you apply your 5 volts here and your 0 volts here, then you could say that it's a negative voltage measured from here to here, minus 5, and you could measure that as a 0. Or you could just connect 0 and 0 here, measure that as no voltage, no appreciable difference, and that could be a 0. Now, there are big problems with this that you have to handle. First of all, it's a lot more difficult to engineer this. It works the same way, use your start and stop bits just fine. But the thing is, this is much more susceptible to noise. Line noise, circuit noise, all kinds of noise. But it's great for going longer distances. You can do something called twisted pair, which is common in Ethernet. You take the these two wires, and twist them around each other so that any noise, any interference from, electromagnetic waves that happen to pass by will affect both of them the same. So, they both might increase or decrease whatever their relative charges are going through, but their difference in voltage between them will stay the same. If you were to measure it relative to this ground, this one might become 4 and this one might become minus 1 relative to that ground. But relative to each other, it's still 5. So that's an option. Another option is something called the Manchester code, which uses rising and falling edges, like I mentioned, instead of measuring the bits in the middle. There's also something called ternary, where instead of having, let's say, 5 volts be a 1 and 0 volts be a 0, you also have 2.5 volts be a 2. And anytime it's 2.5 volts, that means idle line. So it's unambiguous then. It can only be 5 volts or 0 volts on a data bit. And anytime it's 2.5, it's between. So instead of having one start bit and one or more stop bits, you simply have one ternary bit, a 2, in between each byte to resynchronize, in between each group of bits. The main problem with that one is you have less of a difference between the voltages, which makes it more susceptible, once again, to signal noise. You might notice a theme here. Signal noise is a problem. So generally just stick with one of the two methods. You configure your standard 2-wire baud with 8N1 to go over your USB line, and that's convenient. You plug it right in your Arduino, the USB is powering your Arduino, and the other 2 pins are talking to your Arduino. And the clock one is useful in other situations. It's more costly in parts, but it's still nicely easy to engineer. You can even plug the clock line directly into your actual clock and just have a transistor to turn it off. So it might even be simpler to wire at times. But that's the gist of serial. Now, it's important to understand this, but to just get started with doing computer stuff and using serial to communicate, you don't need to understand it. You just need to basically plug in numbers into your little Arduino functions. But if you understand it when you do that, if you at least have grasped this, then as you use your little Arduino functions, you know what's going on and it'll cement it in your mind. You'll think about it. And this will become more and more clear over time as you use your Arduino or whatever you're using that's using serial. So even if you don't need to understand all the bits to create the connection, you just plug and play, that knowledge will come to you. It'll bubble back up and it'll reinforce itself. And then when you are designing your own serial connection, like, you're building a robot and you need to know, I need 2 stop bits instead of 1 because my receiver is a really slow, low-powered thing with lots of signal noise, so it needs extra time to start timing again. The 2 stop bits will give it a little extra time to reconfigure itself. And you're only going to get 1 to 2 stop bits if you use built-in functions like in the Arduino, but if you're writing your own, if you just have your own circuitry and your own microcontroller that's setting the voltages, you can do whatever you want. You can invent your own protocol. You could have 9 stop bits. You can have 2 start bits. You can have it idle low instead of high. You can use ternary. You can use whatever you want. But default, Basically 8N1. 8 data bits, because that's a byte, and that's convenient, and no parity, we've explained that, and 1 stop bit because you're generally not operating in heavy noise environments and we're not using super, super low quality parts. Or old parts. They don't have to be low quality, they can also be old. But generally, just use 8N1 for everything and you're golden. So just keep this in your mind as you start doing electronics, as you start setting up serial connections, and it'll become clear to you over time. And then when you're ready to build your own circuits, you've already learned it. Until then, be seeing you.